We move on to the next speaker, who is Adrià Junyent, the Imperial College, and he will talk about transformation of the top and tail of the energy networks.
Okay, thank you very much. Good morning, everyone. I would like to thank the Endesa Chair and CTOPC for giving me the chance to be here with you to talk about my work. I think the topic of this event is really timely and it matches very nicely with my interests, so I'm very pleased to be here. Before going to the actual contents of my presentation, I wanted to tell you briefly about my research group. I come from Imperial College, and I had some pictures here, but they are hard to see with this screen. Imperial College is in the center of London, and as a university, it has 4 faculties. The biggest one is the Faculty of Engineering with the classical engineering degrees, but we also have the School of Medicine, Business, and Natural Sciences. If you want to come to pay us a visit one of these days, we are in the Exhibition Road close to the Science Museum, so it's easy to locate. And I included the picture here so that you see this is the building of electrical engineering. So this is the first building that you're going to see when you enter the main door of the campus, and you will identify it because it's the tallest and ugliest building of the campus. So there is no way you will get lost. The electrical engineering department have 5 research groups. I'm from Control and Power. Control and Power has 14 academics, 20 postdoctoral researchers, and 65 PhD students. The people in my group have different backgrounds. We have 4 different fields of expertise. There's people from power system dynamics, power system economics, power electronics, and also from control theory. And by combining these fields of expertise, we try to cover 6 different areas of smart grids, power electronics for distribution, HVDC control and design, whole system planning, demand-side response and services from distribution networks, and corrective and wide area control of networks. Now, moving towards the actual topic of my presentation, what I'm going to tell you today is about transmission system support from HVDC. But before I start with that, just let me take one step back and talk a bit about the motivation of this work from my perspective. We've heard about these targets for renewable deployment this morning. In the UK, as well as other European countries, they set ambitious targets for deploying green energy technologies in the coming years. The idea there is to reach, by 2020, 15% of the final energy consumption from renewables, and by 2050, 80% of reduction of the greenhouse gas emissions. Now, one thing is defining the targets, another thing is really finding the way to reach them. There are different ways. It will depend really in a number of things, social aspects, technological developments, the evolution of the economy. There are many variables there. National Grid, the transmission system operator, keeps a draft of different paths, different hypotheses of how things might evolve. There are 4 of them. They keep updating them, following different assumptions. The most optimistic of these scenarios is the so-called gone green, where the idea is that the targets are reached on time. And according to this prediction, by 2020, we would have 24% of the electricity output from renewables, and by 2035, 43%. Now, this will imply big changes in the generation mix, and there is a graph here that is hard to see from where you're standing, but it plots the generation mix in 20 years' time, and it shows that basically the idea is that if we want to reach the target, we have to reduce the conventional generation a lot and increase the renewable generation very much. And basically, this will imply installing a lot of wind power. Now, doing this transition is not as simple as just buying wind turbines. It's not about that. We want to make this transition in an unbundled system where things are owned by different people and we have markets, and this was designed to bring competitiveness to the system, and we want to keep the way things work. We want to be able to do this transition while sustaining really high standards for security and quality of supply. And the thing is, when you introduce a lot of renewables in the system, a number of problems start appearing. Now, when I was preparing the presentation, I tried to do a bit of brainstorming of different problems caused by renewable generation in the grid that we are trying to tackle in different research projects we are working on. And I just wanted to show you briefly some of them because I want to give you the message that the problems appear at all levels in the power system. So in distribution networks, we will have problems of regulation of the voltage because of PV inverters. Voltage profiles in feeders are not going to be as monotonous as they used to be. We have high peak if we want to introduce electric vehicle. We may have unconventional power flows at certain times of the day. If there is a lot of renewable resource, we may have a reverse of the power flow in the distribution network, which is unusual. And there are also problems appearing at really high levels in the power system. At transmission level, we may have problems of high rate of change of frequency because we don't have a lot of conventional generation. We may have low fault levels in transmission grid because we have a lot of power converters rather than electrical machines. And there are a number of problems here that are quite big, and they might become a serious concern in the coming years. Now, the way things have been tackled so far in the past, the way things have been designed and operated, they look like the following. I made just a list here of approaches which belong to what they call the business as usual. Quite often decisions are made based on firm data and worst case scenarios, like trying to account for the worst possible combination of generation at a certain time and what the demand is going to do, etc., and we size things based on that. We tend to do network reinforcement to tackle some problems appearing in the network if you have to add more customers or have to increase the demand, etc. Usually, the distribution networks tend to be passive controlled. The demand is seen as something inflexible. We want consumers to do whatever they please, and we always have to adapt the generation to that. And sometimes we are tempted to do curtailment of renewables if there is a lot of generation and we want to keep some conventional generators still connected to the grid to provide stability. Now, if we follow this path to tackle some of the problems I mentioned before, it may happen that in 20 years' time, the scenario doesn't make any sense because there are high risks of finding the situation where the reinforcement required, for example, to accommodate all these electric vehicle chargers willing to be charged at the same time, is just prohibitive. It's something that is never going to work. Another thing is if we have to depend on reducing the generation of the renewables to keep the system stable, we can be undermining really the efforts we've been putting to decrease the carbon impact of the power system. So there are a number of problems with this approach. Now, these problems become very apparent when you look at the potential underutilization of the assets in the coming years. And it's a bit strange that if we follow the classic approach, we make a lot of effort to deploy renewables in the grid. It may happen that as time goes by, the utilization of the assets that we have in the power system keeps decreasing, and this is not what we want to achieve. Now, there is a chance to do things in a different way, and I'm surprised that no one used this word so far this morning, and the idea is to use the so-called smart grids. And from my perspective, I just couldn't stand the temptation of coming up with my own definition. From my point of view, smart grid should be the combination of information technologies to deal with measuring many things and dealing with a lot of data, combined with power electronic actuators which can provide us good degrees of control over what's happening in the grid. And also, we have to combine that with the smart ways of using them, because the devices alone are completely useless, are very pricey. And if we want to replace an old transformer with a life expectancy of nearly 50 years with high efficiency and really low maintenance, with some power converter that is very likely going to die in 10 years' time, we have to have a very good reason to do that. Now, the message I want to send is that to tackle this challenge, we have to act at different levels of the power system, from the top to the bottom, from transmission level and generation to the bottom at the demand side. And that's why I call this presentation Top and Tail, because it's the title of the name of one of the projects that I've been working on, when we try to envisage how the power system will be in the future, looking at the top, and really the tail. Dealing with these challenges will require efforts from many different fields. And it's not only about electrical engineers coming up with good ways of dealing with the power system, but there is potential for using the demand-side actuators. We want the users to contribute to the stability of the grid, to play a role there. And to be able to do that in a way that works, we really need to understand what are the needs of consumers and how much are they going to be involved in this process. So there's some work for social sciences here too. Now, there are some ideas of things that can be done in the smart grid, more real-time measurement and management of things, role for demand side, larger scale transactions between countries to provide some aggregation effect, as we heard earlier, and also designing new network services so that devices and everything that's connected to the power system can help to the stability of the system. And this is what my presentation is going to be about. New network services. Specifically, I want to talk about some specific type of service that we have been working on that could be provided from HVDC connected offshore wind farms. Now, I want to talk very briefly about frequency transients in the grid. This is something that you find in the textbooks. I tried to explain here what happens when there is a major contingency causing a major imbalance in the power system. If you suddenly have a loss of a big generator in the power system, or if you suddenly have, for some specific reason, a very sudden increase in the load, with those, for example, the TV pickup, they say, for example, if everyone wants to see a royal wedding or something like that, or a football match or who knows what, sometimes there are these effects where the load changes very quickly. Now, when you have this power imbalance, what's going to happen is that the demand is increasing, there is an imbalance between demand and generation, and this extra power is drawn from the kinetic energy that is stored in the mechanical system of the conventional power plants. These power plants are going to start slowing down, and they're going to drag the frequency of the grid with them. Now, the more synchronous machines, the more conventional plants you have, the slower this transition happens. And the smaller the change in the imbalance, the slower this transition happens. Now, the system relies on this inherent behavior of conventional power plants to stabilize the system in the very beginning of these transients, because in the first few seconds there is no centralized control to take decisions. Soon afterwards, some of the generators have what they call the primary control, where they tune the power output of the power plant, which means that they have to be running with a certain reserve to compensate for the imbalance. And what they manage to do is to speed up the generators again and keep this drifting of the frequency from moving on. Afterwards, in a matter of tens of seconds, the frequency of the grid may stabilize, but may stabilize with a certain error. But because there's been some time already, the transmission system operator has time to take decisions, sometimes with automatic procedures, sometimes with manual emergency commands, etc. So they have some time to schedule new generation to bring back the system to an acceptable situation. Now, if we replace conventional generation with offshore wind power, these things are not going to happen because we are operating them nowadays in a different way. In this particular work, I wanted to focus on what's happening in the very beginning, which is something which is of great concern for the transmission system operator in the UK, and it is in other countries as well. If we want to implement these frequency support services, and as I mentioned here, there are different time scales. In an offshore wind farm, we have to take into account different things. For the long-term response, if we want wind farms to be able to boost their power output in the range of 2 hours time and things like that, we will have to discuss about the sizing of those generators, because we want to run them with some headroom so they can change and increase the power output at will. This is something we have to take into account. There is some economic analysis to be done, etc., etc. If we want to go to the smallest time scale, to this very quick response, actually the matter, you have to take into account the dynamics of the wind turbines, the dynamics of the HVDC system, and a series of things. So it's quite a tricky problem, and this is what I want to tackle here. So imagine that we have an offshore wind farm connected through HVDC to the mainline grid, and something big is happening here. We want the turbines to react very quickly, and what they have to do is to boost their power output following the derivative of the frequency of the grid. Now, having wind turbines do that when they are connected in the mainland grid is something that has been studied in the past. I think the first proposals come from 2003, 2006, something like that. And it's something that some manufacturers are already advertising that they can do. Now, when the wind farms are offshore and they are really far, 200 kilometers from the shore, they are not aware of what's happening on the AC grid. So they have to be told. And there are different ways of doing that. Now, we looked at the literature before starting this, and we saw different approaches. One of the ideas, the most basic one, is to measure the contingency here in the onshore converter of the HVDC link, calculate how much power needs to be injected to the grid to provide this support, send the message to the wind farm, and then the wind farm controller is going to issue commands to the individual wind turbines and somehow provide this power output. Now, the problem with that is that there are many steps involved in this process. So by the time the power goes back to the grid, there is a certain delay. And this wouldn't be a concern possibly in some systems where there's a lot of synchronous generation and a lot of inertia. But if we want to go to a low inertia scenario, this might be a concern. There are people who are worried on what's going to happen in the first half of a second. So this is something very quick. Now, there is another way of doing things that have been shown in literature, and the idea was to keep the turbines unaware of these sudden events, leave them time to react if they have to provide response for primary support or something for longer term, and provide this energy boost in the beginning entirely from energy storage in the HVDC link. The HVDC link is a DC bus. It has some capacitors there. There is some energy stored. You could oversize those capacitors or install maybe some batteries or something to be able to do that. The good thing about that is that the response can go to the AC grid really quickly. The bad thing about that is that the oversizing that you might require can be high. And you may have a lot of energy stored there, just sitting, waiting for the day in like 10 years' time when there is a major contingency and they have to boost this power. So it doesn't look very appealing. So what we tried to do is to combine these two ideas and come up with something we called the blending approach, which is blending together different sources of energy. So we want to use a bit of energy from the HVDC link of the converters to provide a first package of response towards the AC grid to keep the rate of change of frequency from going crazy, and then send a command to the wind farm in some way so that the wind farm has a bit more time to react. Now, so basically what we do, we have to change the voltage of the capacitors of the stacks of the converter or the voltage of the HVDC link, and we're going to take energy from there by lowering their voltage, and at the same time we're going to command the wind farm to start delivering some power. Now, to compare the three methods in a fair way, we came up with the same framework. We analyzed them using the same tools, and here are some results that I showed using a simplistic model just to illustrate how the different methods work with a converter which is the same for all of them, okay? So the comparison is not entirely fair because, as I mentioned, the sizing requirements for these different approaches would be different. Now, the first column there is about just sending the command to the wind farm. The second one is using the energy stored in the converter alone, and the third one is about combining both ideas. It's hard to see from where you are, so I'll try to explain. First is voltage, current, and power. I think the most interesting part here is power. I have plotted there the power of going to the AC grid and the power coming from the wind farm. In the first case, we have like a pure delay. We have a time delay between we send the command and we get the response because we are issuing a command which is taking some time to reach the wind farm, and it takes some time for the power to come back to the grid. In the second method, the wind farm is kept unaware, its power output doesn't change, whereas the power going to the AC grid changes immediately. And in the third In the third method, which is the one we propose, the response towards the AC grid is sudden, is very quick, whereas the wind farm ramps up slowly. If you see what happens with the voltage of the converter, it gives you an idea of how much energy you are using from the converter. So in the second method, the voltage would have to keep drifting while you're providing the response, whereas with our method, it would settle because we are relying on the wind farm to provide the rest of the energy required. Now, there are many design parameters here to take into account. This is not straightforward to tell whether this is good or bad, because it depends on how much energy we have in the converter. It depends on how quickly we have to react towards the AC grid. It depends on how slow the wind farms need to react or would like to react. It also depends on how much energy storage you can place in the converter. We try to quantify how the method where you use only the storage in the converter compares to the method where you combine both sources, and I think the results were quite promising. We tried to take parameters, reasonable parameters for the energy stored in converters, the voltage margins that you usually have in HVDC links and HVDC converters, the rate of change of frequency that you may have to handle in the AC grid, and doing a bit of parametric sensitivity analysis. It looks like our idea is not silly, and it looks like the other idea is not silly neither, but it's just that it will require really a major oversizing of power converters. Now, to illustrate how good this thing was, we ended up coming up with a dynamic model of the AC system, and we used to benchmark or to show the benefits of our approach. We used the Kundur system. It's a system with 4 machines with 2 areas connected with 2 long tie lines, and what we did in the simulation was to replace one of the generators by an offshore wind farm. And we tried different scenarios. The original case, the well-known Kundur system, a system where our wind farm only provides primary support, which means that in a matter of few seconds, the power coming from the offshore wind farm is going to kick in. Another method where we add this inertia support to the converter. And the third method where we disconnected to the primary support to just see what is the effect of having inertia emulation. So in the first analysis, we just wanted to show that by providing inertia, the rate of change of the frequency in the beginning of the contingency can be kept the same way as it was in the original power system with synchronous generators. Whereas if we remove the inertia emulation, we have a rate of change of frequency which is worse. And it's very easy to calculate how worse it will be, because with very basic equations you can get that. Now, if we remove the primary support, but we still have the inertia, the beginning of the transient is the same. But then this recovery of the power system is a bit delayed. So we may get frequency values which are lower. This is also a concern sometimes, because conventional power plants are meant to operate at the range of frequencies. You don't want the frequency of the grid to drop to a value that is too low. Finally, if we compare what would be the power output of the wind farm if we have both things, primary and inertia, or if we only had inertia, this is what we get here. With primary and inertia, we have a sudden boost in the beginning, and then a sustained power output due to the support required to keep the voltage, the frequency of the grid steady. If we only have inertia, inertia is something which plays a major role in the beginning of the transient, but not afterwards. I have some additional graphs here, but I think I'm running out of time, so I think I will skip unless someone is really interested on that. So summarizing, I think this approach I think there is an application for this in grids where there is a big concern for low inertia scenarios, where there is a desperate need to keep the rate of change of frequency low. There might be an application for this. Next steps that we are doing, we're trying to analyze this in more realistic models of the power system and of the power converter. If you want to read a bit more about that, we have a paper, and of course you don't have time to write it down now, but if you search for blending HVDC energy, I think you're going to find it very easily. So that's everything from me. Thank you very much.
Thank you very much, Adrià. So we have some time for a question. Yeah, in the back.
Right. I don't know if I missed it out, but how much do you have to oversize your converter capacities in your method?
Sorry?
How much do you have to oversize the capacitors when using your blending method?
Yeah. It depends on the voltage margin that you have. To try to be fair try to be fair in our studies, we assumed a rate of change of the frequency up to 2 Hz per second. We assumed to have a voltage margin to be able to change the voltage up to 10%. And even though we've made some studies in the results where it's only 5%. And it also depends on how much time do you give to the wind farm to react. If you give the wind farm a lot of time to react, you need more capacity. If you don't need, if you can allow the wind farm to react very quickly, which would undermine this approach compared to the first approach, then you'll need very little capacity. Well, in this case, in the simulation scenarios, we used the same amount of energy stored that you have in a conventional HVDC link, so we didn't have to oversize the capacitors, and we took that 10% of margin. If I remember well, for this rate of change of the frequency and to emulate an inertia time of 2.6 seconds, but I might have to check that again. I think there is something common, which is how much overrating of the power do you need, and in this case it's a 10%. So for a 50 Hz grid. So there are some things that there is a price for this. This is not going to come for free. We are trying to compare it with the other methods, and again, for these things to become a reality, someone will have to pay for these services. There is a market for other types of reserve. For this type of reserve, there is not still a market or a defined rules of how it should be done, but the ENSOE and other entities have already expressed interest in this kind of behaviors.
Okay.
Thank you.
Okay, thank you. There's another question. Quick.
You just talked about the interest in possible market for inertia. Do you think it's going to be a market, or do you think it's going to be managed by a grid code? And what would you prefer?
Well, yeah, well, good point. I think maybe you're right. Maybe it would be like the right-through requirement, something that has to be there. I'm not sure what is the best option, really. I mean, this is a regulatory question. I don't think I'm an expert on that.
No. Okay, thank you very much. One question, quick question. It's
the tricky one.
The trickiest one. What do you think? Who will win, the top or the tail?
Oh yeah. Well, because all my work is focused on the top, I would say the top.
Yeah, for
but,
sure.
I think there is a role for both sides, really.
Yeah. Okay.